So, welcome to lecture 6, compressible duct flows. Let's just see how we start. So, in our previous lecture, we kind of gave this trajectory of looking at jet engines in supersonic flows, or propulsion devices in supersonic flows, and the idea that we would be look at the inlet. And then as the flow passes through the inlet, there's a change in cross-sectional area, so which we'll cover today. There's the addition of, we've got compression, there's change in cross-sectional area, there's compression, then there's combustion, expansion and exit. And so what we're going to cover today is the middle part of that story, kind of jam in the sandwich, which is the influence of change cross-sectional area, the influence of changes of heat, either the addition of heat due to a reaction or condensation or some heat transfer process. So duct flows are what we're going to do today, and essentially we're going to be looking at, in a general sense, is why is a rocket nozzle shaped like this. That's going to be lecture 6, which is changing in area. There's up an area which changes with distance. And lecture 7 is going to be two things actually: the addition of heat, additional change in heat, and the second thing is the effect of friction. And as we've mentioned in actually lecture 1, if we add heat, what we're essentially saying is that momentum's conserved, mass is conserved, but energy is not conserved because it changes because of the addition of heat. And so this is a Rayleigh flow. And when we've got friction added, commonly in very long pipes, or when there are obstacles in place, then energy is conserved, mass is conserved, equation state applies, and so this is what we call a Fano flow. Just to kind of describe the general utility of the 1D stuff we've done, so when we've done work on, for instance, tsunamis, the influence of buildings on tsunamis, this comes through, can be expressed in terms of a Fano type problem, with the possibility of jumping from one state to the other. And so although we're going to deal with a one-dimensional problem, we're going to see a range of complexity of solutions, which kind of demonstrates the complexity of this problem. Fascinating. The solutions themselves, although one-dimensional, just give us a general insight and reasonable predictions of what happens in reality. Obviously, slight differences if the 1D analysis don't apply. And lecture 8 is when we're dealing with exit flows, either from a gas turbine engine or a rocket. And so we'll discuss those. So, but today is, how we get here, is our lecture 6. So this whole duct analysis, still talking in the general case, is one in which we've got a whole class of problems where we've got a flow in a duct whose cross-sectional area may be changing, and the change in the area is, or in the lateral diameter, for instance, is small. And what we really mean by that is the change in diameter is a magnitude change in diameter is a lot smaller than what it's been the distance. So we're dealing with long ducts whose cross-sectional area is doesn't need to be fixed, but generally it's either going to be rectangular, circular, or conical. And there are 3 types of processes, just kind of recapping this kind of lectures 6 and 7, that are important. One is where we've said is where the area changes, cross-sectional area change is important. Kind of larval nozzle. Other ones when frictional force is important, where momentum is not conserved, and heating and cooling are important, where energy is not conserved, as we've said before. This is our lecture 7, and this is today's lecture 6. Now you can, although we're going to deal with these separately, we're going to apply a linearized analysis that can be a non-linear analysis that can be all combined together to incorporate all these effects. So what I want to do before we start to deal with the science, I just want to kind of recap a couple of points that we've made in previous lectures where we talked about how we kind of solve problems in fluid mechanics. And so what you've learned so far in your year one is that we applied what we call an integral approach to analyze fluid flow problems. And this is an idea that we can think the state of a flow in, for instance, region 1 to a state of a flow in region 2 by understanding those changes that occur in between. It's sometimes called a zero-dimensional model because essentially you can use an integral analysis to try and find out what is conserved, it's zero-dimensional because it doesn't tell you what's going on in the middle. It just tells you the relationship between state 1 and state 2. The other approach, which is much more general, the integral approach which you applied before in year one, is very useful in certain scenarios, calculating forces on things, calculating the total change in entropy in a system. Is sometimes not very useful when we're looking at changes in time and over distance. And for this we use a differential approach, which you've looked at more in your year two. Sometimes you call this a 1D problem. Essentially you've got some state variable, maybe pressure, maybe reduce everything to one-dimensional, so it's real, and remove time, and you're looking at how, for instance, fractional changes in pressure vary along the pipe. In this particular case, you'd probably call it a one-dimensional model. We're going to apply both problems. Both are applicable. So integral approach sometimes doesn't work. It just depends on the complexity of the problem itself. But we're going to apply both to kind of see that their general utility. So we kind of met these before in your kind of year two. You met the differential approach. This is obviously your states. We're dealing generally with viscous problems in this course, so viscous effects disappear. And the bottom thing is an integral. Is this just in general an integral approach which you've used before too? Just to recap. Sorry for the going on Gower Street, very noisy. So just to recap on reference state. So I think all of our lectures so far we've used a stagnation reference state. So when we looked at flow past aerofoils, we've looked at expansion fans, we've used stagnation values which are useful for isentropic processes. Stagnation temperature, obviously indicated here, is value for adiabatic flows, but stagnation quantities we've used previously. But for the types of problems we're going to look at next, which are duct flows, we use the critical values, which is the values that will occur when the Mach number is 1. So in duct flow, the potential for the flow stopping is well, I mean, for lots of reasons it won't occur, but the potential for it becoming sonic is present, and so we need to. This is a more convenient reference state, and we'll see that kind of emerges from the analysis. So one way to look at the duct analysis problem, which is this flow in a pipe whose cross-section area is changing, is simply just apply the conservation of mass by combining what we've discussed before in the previous slide, what we've talked about the stagnation values, and this zero-dimensional approach, integral approach, is a simple way of calculating or resolving the problem. It not very complicated. And this idea is really quite simple, which is to say rho times u times cross-section area is a constant. So what's the purpose of this calculation? So I'll just go back, is that in order to look at these duct problems, we're really trying to find the relationship between the variables as we move along the duct. And the key variable is obviously the description of the state of the gas flow, which is characterized by the Mach number, whether it's subsonic, sonic, or supersonic. And so the key that the thing that we're aiming to get is this relationship between the cross-sectional area of the duct A and the Mach number. So we can apply conservation mass. Rho UA is constant, and we don't know what that constant is at the moment. It will be determined by an initial state. Let's just say that state is U star rho star A star. We don't know. We know what a critical velocity is. We can estimate what that's going to be. That's going to be gamma RT star. But this is obviously a kind of a value that may not exist at all, but is a kind of floating variable. So we've got our rho UA, and we set that equal to a constant, and arbitrary reasons we set that to be U star rho star times A star. A star may or may not be physical. We'll see in a minute what consequences is. Now we're going to assume that the flow is isentropic. Reasonable assumption. If we do have a duct flow and we do have a shock, a normal shock, then the flow is isentropic here and it's isentropic here, but it's not here. Yeah. So even this approximation can be used quite generally in places where shocks occur, but not across the shock itself. So before and after are pretty okay. So what we're describing here is an analysis that works, if you like, in this region over on the left hand side. Yep. And the region on the right hand side, but not obviously across the shock. And so one of the great things about fluid mechanics is your ability to stitch together solutions that build up a physical picture of what's going on. So we know rho UA is constant, and so we know from the previous slide, we know the relationship between P and P star, and we know the relationship between T and T star, an isentropic process, so we can substitute those in. Just noting that to get the relationship between U, and so these P over P star, T over T star can be expressed in terms of functions of Mach number. Now U is a bit different because it's we've got to express it in terms of something simple, but U equals basically temperature times local speed of sound, which is T gamma R times Mach number, and divided by gamma RT star. The critical value when at the U star of Mach number is obviously 1, and so that's how we find the relationship between U star and Mach number. T can be expressed in terms of the Mach number. So we put those relationships together, and what we find is this relationship between area and Mach number. Let's see what it gives. So here we have this relationship, and it's an analytical expression, really quite simply put together. And the value of A star corresponds to when the Mach number is 1. Now, the Mach number may or may not be equal to unity in any part of the flow, but it's a convenient reference state. So on what we got on the vertical axis is the cross-section of the pipe divided by A star, critical area, versus the Mach number. This curve has a minimum at the Mach number 1, at which point dA is, or dAdm is equal to 0. So this is a really quite fascinating element of the story is that this curve has the potential for multiple solutions. That's the first thing. So if we had a cross-sectional area, let's say A over A star is 3, then there's a potential of having either a supersonic, a subsonic, or a supersonic flow. So the first thing is a multi-value, and this is going to one of the reasons why we're going to end up a lot of really interesting types of solutions. Now, the first thing is that we can start to understand what is the consequence of a changing cross-section area on the Mach number, just simply from this curve here. So if we take a pipe and it's compressed, pressing the flow, and the Mach number is let's say less than 1, so subsonic flows, then if dA is negative and we're on the left hand side of the curve, this is the subsonic side, then if the A decreases, dA is squashing flow, then the Mach number goes up. So that's kind of intuitive. The flow gets squashed, area goes down, velocity goes up. If we do the opposite, if we have a subsonic flow and we expand it, then of course area is increasing, so dA is positive, Mach number is still less than 1. What happens to the Mach number? Well, we stand here, the area decreases, so we're going down this, we're going sorry for that interruption, the police car was a bit too close to the office. So if we expand the flow, the area increases, and what we'll end up doing is we're going up in this direction and the Mach number decreases, and that kind of makes sense. Let's have a look to see how that picture changes as we work at supersonic flows. So supersonic flows, Mach number now is bigger than 1. We've got an area which is now decreasing, we're kind of squashing it. And so we're at this curve, area is increasing, so dA is positive. Sorry, dA is, we're squashing the flow, dA is negative, so we're coming on the left hand side, so like that. And what we see here is that M decreases. So opposite to the case of a subsonic flow, that's right, subsonic. And the reverse, if we expand the flow, so now dA is positive, M is bigger than 1, what happens? So we're on this curve here, A is increasing, so A increasing is going up, and so what happens in this case is the Mach number goes up. So once the Mach number is supersonic and we expand the flow, what will happen is that the Mach number will increase further. And this is quite important, this idea that if we squash the flow subsonically, Mach number goes up, and when we expand it, when it's supersonic, the Mach number goes up. So this is one way that we potentially got of creating a supersonic flow. The challenge, obviously, or the important thing is obviously here, is that the Mach number is unity when the changing area is 0. And so this is how supersonic flows are actually generated. This is a picture of a laboratory test, standard lab test. And so what we have here is a reservoir of gas. So in the past we used to have one downstairs in the mezzanine floor in the fluids lab, and the tanks, very old, from the 70s, very large. They would have been probably, it must have been 200 litre, two 200 litre steel tanks, ramped up to maybe 50 bar. And so what we do with the reservoir, we charge it up to a high pressure, maybe, I don't know, 50 bar or something, and we discharge it through a small constriction. And the critical thing in all of this is the fact that the flow is contracted and then expanded. Providing the area of the throat is small, so here we have what we call a throat area and an exit area. Providing the area of the throat is small, the back pressure is low. Remember, it is the pressure difference between the reservoir and the back pressure, or atmospheric pressure, which is essentially pushing or sucking the gas through the system, drives the flow. But to cause the pressure, in order to cause it to be supersonic, we need to contract it first in order that the Mach number goes up. You need to contract it sufficiently that it's going to go through a sonic state when at the throat, Mach number 1, and then as we expand it, the Mach number increases further. This is an example of a case where we've got idealized conditions where the back pressure and the exit pressure are equal, which means that what we have is basically a slip surface here where the flow is moving and outside it's stationary, and there's no shocks or expansion fans. Now, what happens with these kind of reservoirs is that the mass is lost, and the pressure differential is reduced. Now, it won't reduce continuously, and it won't change the mass flow rate until the flow is no longer choked. So we'll discuss that next. So the alternative approach to using this integral approach of basically saying rho times u times a as a constant is to start to look at differential changes in Q variables. And you've met that in year 1 in your differentiation course, when you're looking at think of experimental errors and you wanted to find out the error in the measurement of the current when you're measuring estimate of, I think, the resistance when you're measuring current and voltage in a circuit. And the idea is that you have a relationship between your three variables, your variables. You take the log of it, and then you take the differential. And as soon as you take the differential of for instance, log rho, then this becomes a d rho over rho. Same as u becomes a du over u. This allows you to find a relationship between fractional changes in one variable compared to the others. The way you construct a differential form for relating one state to another in a duct is that you will have to go through the conservation of momentum in a differential form. It's isentropic flow, so P equals rho gamma times K. And so you would take these three relationships, mass, momentum, and isentropic. You'd find the differential relationship between these variables. Remember, we're looking at dP over P and d rho over rho. And you'd combine them to find out the relationship between how m varies, fractional changes in m, fractional changes of a. In reality, actually, most of the time, what you do is you find out, you could do dMdA, which would be probably two of that, yeah. But in general, what you find is that m squared appears everywhere in most places. And so what you're really trying to do to make the algebra easier, you're looking at different changes of m squared. So if you find this, you can put everything here, on the left-hand side, keep dA over A on the right-hand side, and then you can integrate. And so the consequence of a change of area, going from area 1 to area 2, can be determined by this integral relationship, which is this integralist rather complicated formula. And the integralist complicated form does have a closed analytical form. We met it on the previous slide. But now, that's how you do the differential approach. Equivalent to the integral approach, slightly more complicated, but equivalent. The main thing about, or the main interesting thing about this class of problems is that the flow has, I'm just trying to think of what's under there, so I think it must be P, it must be a value of 1, and that must be PB over P naught. PB is the back pressure, P naught is the reservoir pressure, and this value must be 1 underneath my video recording. Now the critical thing about this type of flow is that providing that the flow through the system is determined by the pressure differential, pressure ratio between essentially the reservoir and the back pressure. Now, if the reservoir is the same pressure as the back pressure, then of course there's no pressure differential and there's no mass flow. So everything to the right of this 1 means no flow, nothing going on. Now, if this is a vacuum, then essentially you'll be pulling through or pushing through the material, and what you end up with is this rather interesting scenario where the flow is choked, as in there's no mass flow can go faster than through this. What you end up essentially saying is that the state of the flow in the vicinity up to the throat and a little bit beyond, depending on what the pressure differential is really independent of the pressure differential if it's in a choke state. Now, as the back pressure decreases, so we're moving to the right here, there's no change in the mass flux until we reach a point at which the flow becomes the sonic flow condition at the throat is lost. What you'll end up seeing is you're seeing the flow, we're going to see in the next slide, but the flow will start off as supersonic at the exit, then it will become sonic, then you'll end up with a normal shock. That normal shock will regress back to where the throat is, it'll become weaker and weaker and weaker, and then once it meets there, the strength diminishes, it becomes sonic on the left and the right. And once it becomes sonic on the left or right, then the condition of being choked is lost. Now this has quite important implications, as you might imagine, for a rocket. Essentially, what you're saying is that you cannot push more mass through that nozzle or that throat, and so you need to some way sometimes of having designing it so that it is able to receive. First of all, that it is choked. That's going to be quite important for a design of a rocket. You're going to see in lecture 8 that you need the exit flow to be supersonic in order to get maximum thrust. And supersonic has a requirement that it's got to be choked, and of course has implications for mass flux, so it's all kind of related. The types of solutions you get out of this is really quite spectacular. So just combining that analysis we've just done with normal shock analysis, you can predict or describe all of these extremely complicated phenomena. And so we're going to discuss those as we proceed. So we're just going to discuss actually the evolution of the pressure distribution through the, that's my stylus. We're going to discuss the evolution of the pressure distribution along the channel as in time we decrease the back pressure. So what we're keeping here fixed, we're going to say we're going to imagine the reservoir is a constant pressure, the back pressure, and we're going to decrease it. So if the back pressure and the reservoir pressure are the same, then of course the pressure differential is 0 and there's no flow. If we have a small difference in pressure, then what will happen is the flow will remain subsonic. So this is kind of curve A and B. Subsonic. And this will drive a subsonic flow. And we met before that, well, we know from kind of intuition that when we drive a flow through this constriction, the flow will get faster as it goes through the throat. Bernoulli's equation gets faster, pressure drop, and so we'll see a reduction in the pressure at the throat. We see here, this is coming down and then coming back up. And as we increase that pressure differential between the reservoir and the back pressure, in this case we're pulling down the back pressure. It's probably an easier way to think of it because the left hand point is it's just an easy way to think about it. Then what happens is that the flow pressure differential becomes larger and larger and larger, and so what we end up doing is just bring that down. Now when the pressure drops below 0.58, at which the flow becomes sonic, yeah? And so but if we're just above that, we will still recover and the flow will be sonic all the way through. Now if we reduce our back pressure further so that the throat pressure is below the sonic state, then what happens is, not below, but if we reduce the back pressure, then what happens is that the exit flow still becomes subsonic, but it must somehow match onto this sonic state condition. And so what happens is it continues on this isentropic curve, and there is a point at which it jumps up and matches back onto the nice, and that jump is through a shock. And so in this particular case, the flow becomes supersonic with a normal shock jump, very weak at first, back onto this subsonic branch. As the back pressure decreases further, then of course what happens is that the shock moves away from the throat, it becomes stronger, and we end up with a sonic state, a supersonic state here, normal shock or shock, and then a subsonic range afterwards. As we decrease the back pressure even further, then we end up with a case where there's a normal shock at the outlet, and if we decrease it further, then we've got all sorts of flow conditions that might appear. Now, if, for instance, now what happens, as you see, is that everything collapses onto this kind of unique isentropic flow curve, and that flow is then independent, and the flow and the normalized pressure distribution becomes independent of what you're doing outside and downstream, outside and at the back pressure, providing back pressure is low enough and the throat is small enough that you'll end up with a choke state flow condition. And there are three cases of this, all reasonably straightforward. One is that the flow is subsonic everywhere, and in this particular case the exit pressure equals the back pressure. One case B, is where it's choked but there's a subsonic outlet and it's characterized by a shock some point between the throat and the exit. In case C, which is as a supersonic outlet, and the back pressure and exit pressure might be bigger or smaller. That depends on how much expansion you're doing. Case A and B, these are kind of easy to deal with. Easy. You can see they're easy because they both follow this isentropic pressure distribution curve. Case B is difficult because there's a normal shock. Since the solution is really driven by the pressure, your challenge is to determine the location of the shock, and that has to be done intuitively. So case A, subsonic flow, relatively straightforward, isentropic all the way through. Since it's isentropic, we know what the exit pressure is. It's equal to the back pressure. We know a relationship between P and the reservoir pressure. We know that's a function of Mach number, and so we can determine the exit Mach number. So the exit Mach number will then be, in this particular case, it's determined by P0 over PB. Now, what we're trying to find is really how does the Mach number depend on X, which is a distance along the throat. Well, what we know is we know a relationship between Mach number and area, which has got a star in it. We don't know what that is at the moment. And we know a relationship between area and distance. And so what we do is we use our area and Mach number relationship to try and determine A star. Remember, we know that A over A star is a function of Mach number, and at the exit, since we know the area is equal to the exit area, we can determine what A star is, and so this gives you the solution, and that's the process by which you solve. And so this is a relatively straightforward case. The mass flux can be determined by any point. Usually you do it at the throat because it's relatively straightforward, or in this case the exit case. Case B is a bit more challenging, as I said, you're constrained by your back pressure, PB. You've got your inlet pressure, reservoir pressure, P0. You know this, and so the challenge in this is that you don't know where your shock is. And so what you typically do is you guess where a shock might occur. You follow this curve down, you guess it occurs here. You determine, you've got your Mach number before your shock. You can use your shock analysis for Mach number afterwards. You know your Mach number, then you know the pressure, and then you can follow that through. Now the point about this is that A star region 1 and A star in region 2, they're not equal. Yeah, so you've got a bit of work to find out how those solutions vary in those two cases. Now the main point about this kind of analysis is that you take on board the fact that in the first part of the solution, where you're looking at the flow to the shock, up to the shock, exit, which is equal to PB. This is subsonic. This is supersonic. This is subsonic. And so in this region up to here, what you do know, what helps you out, is that the critical area is actually the throat area, because there is actually in this case there is a point at which the Mach number becomes unity. Not the case with the subsonic flow everywhere. The other point to note is actually the stagnation pressure decreases after the shock, and the constant is different in those two regions. Case C is relatively straightforward. It's exactly the same as case A, where we've got subsonic everywhere. Here we've got subsonic becoming supersonic, and again we can determine the relationship between the exit Mach number and PE, and we can determine the relationship between the exit Mach number and the ratio of areas, and we need to get the exit pressure from the solution as well. So they have to be obviously consistent. So if you're given the exit area, and you're given the throat area, then you can find out what the exit area is going to be. So there are two kind of conditions, three kind of conditions. There's the possibility the back pressure and the exit pressure is the same, which is called design pressure. And this is quite important for determining whether the presence of parasitic drag from rockets. If the exit pressure is bigger than the back pressure, so we've got our nozzle, got exit pressure is bigger than the back pressure, well, it means that we haven't expanded enough. And as you expand, the pressure goes down. The velocity goes up, the Mach number goes up, the pressure goes down. And so and so this is called an underexpanded. So you've not expanded enough by going through the nozzle in order to reduce the exit pressure. If the exit pressure is less than the back pressure, then this is a case where you've overexpanded, and so as you expand, the pressure goes down, and that's the challenge. These obviously have implications for the kind of flow structures you have coming out at the end, which we'll discuss in lecture 8. So this kind of concludes our lecture 6. If you can go through the tutorial questions, they're relatively straightforward, especially using the compressive flow calculator, and the in-class tutorial sheet should put you in good stead to go through all the problems. Next week we're going to be doing Rayleigh and Fano flows, and the week after that we're going to be doing the exit flows. Thank you very much. Bye bye.